So today, like, I like to introduce a decision tree, which is one of the very, very popular machine learning algorithm. And then it's pretty kind of old. It's nothing, brand new about it. But the reason I wanted to do this is first, it's actually kind of cool. The visualization you can get out of it is very intuitive for you to understand without any sort of like knowledge, background knowledge of the statistics or anything like that. So it's useful. But also, there's another machine learning algorithm called random forest. Or like actually, there are a bunch of tree-related machine learning algorithms, like something like XGBoost and so on. But those are all based on actually this decision tree. So I like to introduce the random forest, which is actually the more, I think it's more important topic. But let's start with the decision tree to get understanding of like how the tree in the machine learning world works. Then like, I think next week I'm going to introduce a random forest, which is basically based on this decision tree. Okay, so just a brief summary of the whole data science sort of like a workflow. So like you always have like a question or the problem that you want to address by using data. So you always start from like a left-hand side of questions. Then like you find the data to be able to address those, answer the questions. But then the data you usually get is always kind of like messy. So like you want to do the data wrangling. And then if you want to understand data intuitively, so if you use charts or whatever to visualize the data so that you can understand with your eyes or intuition. But then like your eyes or intuition has limits. So therefore that's where the analytics comes in. So that's where like statistical machine learning algorithm. And then the topic of the decision learning I'm going to be talking about today is this area, the analytics area. And then like after all, like basically you get the insights, then like you go to the communication by using dashboard, notes, slides. So this whole green background area is where like you can do with Exploratory. But today we're going to focus on this analytics piece of the box. Okay, so decision tree is really a series of questions you can ask data to basically like get that answer or predict like sort of unknown values. So let's imagine like we have the US, we have baby data, right? So each row represents each baby, and then we have information like weight pound, which means like what are the pound that when the baby was born, right? And then there's another column called plurality. And that is basically like if the baby was a single baby or a twin or triplet and so on. And then the last column, which is colored by the purple, is premature. That means is this baby was prematurely born or mature born, right? So when it says true, that means this baby was prematurely born. I think according to WHO, I think the baby was born within 37 weeks, less than 37 weeks, and then that is considered as premature. So anyway, so that we have that information. And then imagine there was a new baby come, and then we don't know if this baby is premature or not premature. So how are we gonna answer the question? And so that's the question here. So there are many algorithms we can use, but one of the machine learning algorithms you can use is a decision tree to build a prediction model to answer the questions. So how it actually does, instead of like just using it, before using it, I want to kind of like start a little step by step to explain how the decision tree works. So just imagine like we have these two variables. I'm going to start using this word called variable that basically very similar to the columns in Excel or any table, right? So anyway, so we have the plurality and the weight pound. Those are the two variables. And then like we try to visualize this data. So think of each dot or circle here is a baby, a given baby. And then his, her weight pound is 7 and the plurality is 1, and then like you get the position of that each baby. So now we can color each baby based on whether a given baby is prematurely born or not premature, meaning just mature, right? So here, the red color are the prematurely born baby, and then blue color is a not premature, okay? So then basically, like we want to draw a few lines. I mean, like as less as possible, but a few lines to divide these baby into different buckets or different groups. Okay, and then so the question is, so where should we draw the line? So let's say like weight pound. Should we draw the line around like between 5 and 6? Or for example, when we focus on the plurality, should we draw the line between 1, 2, or where should we draw the lines? And we can draw the lines multiple times. But the point here is can we separate these babies into different groups by drawing the straight line either on the x-axis, either on the or y-axis. And then if we can do that, then that will be the conditions that like we can use to predict, even like if we don't know if the baby is premature or not. But as long as we know plurality and weight pound, then we can predict if the baby is premature or not. Some of you guys might have started thinking like, hey, isn't this kind of stupid? Because like if you know the weight pound, of course you know the baby is premature or not premature. So yes, I'm pretty aware of the stupidity here, but just to make this whole thing is easier. So just bear with me. Okay. So now let's draw the line around like between 5 and 6 weight pound. Right, so like let's say like weight pound is greater than 5.5, and then like we draw that here, because like it seems like if we do it, then like any baby greater than whose weight pound is greater than 5.5 is we can say, hey, these babies are not premature, right? And then like let's add another line around like 1.5 of plurality, right? Then by doing so, like we can say any baby greater than 1.5 plurality and less than weight pound 5.5 pound are more likely to be premature because it's all red color, right? So I think that's so that now like we created 3 different groups, and then 2 of them it seems to be like kind of easy to predict or because all of them are either premature or mature. Okay, so like we can create these groups, and then based on like a majority of that group, so we can color it. So like we have basically 2 blue groups and 1 red group, right? Like red right hand side bottom, and then the top group. That's easy because everybody is either blue or red. And the tricky thing is the left hand side bottom. It's like but majority is like 3 babies are blue and 2 babies are red. So like we can say like this is like a blue group, which means not premature group. No, sorry. Yes, that's not premature. Okay. So just to kind of clarify this, because these 3 metrics are going to be important like when we start seeing a decision trees visualization. So like I want to actually kind of like set this clear. So 3 things. So number 1, which is the color in this case, but also the category. So this group, like focus on the top group, okay? The top group, which is greater than, whose weight pound is greater than 5.5. So this group, that majority of the people, or my baby in this case, are not premature because it's blue color, right? So if you ask the question, hey, are these babies premature? The answer is no, right? So the majority are no. And then the ratio of premature or percentage of premature baby in this bucket is 0%, okay? And then the last one, the ratio or percentage of all the babies. So when you have like, I'm not sure, like I haven't counted yet, but like, let's say like 30 babies are here, then how many of those 30 babies are, belong into this group? So like it turned out that's 40% of the baby. So that means for 40% of the babies, like we can predict, always saying like, hey, these guys or these girls are going to be not premature, and 100% of the sort of like probability or 100% of the accuracy here, right? So let's go to the next one. So this is a one, like I said, it was a little tricky because they're mixed. So it's like blue babies and red babies, premature babies and the not premature babies. So if you ask like if this is a premature, the answer is no, because just majority are no. So you know, it's not 100%, but it's the majority is no. And then the percentage of premature babies in this bucket, because the basic question here is the baby is going to be premature or not. So we ask the premature, then only 40%. So it's a minority, but 40% of the baby are premature in this group. And then like how many babies are in this group compared to entire babies. So that is 20%. So 20% of the baby belong into this group. And then, you know, their status are like premature is no, and then ratio percent premature is 40%. And then let's take a look at the last group, which is the red group. And then like, if you ask questions, hey, are these groups, should we consider premature or not? Then the answer is yes, because everybody is red, right? But precisely, it's actually majority is the yes, so like we can consider this group is the yes group. And then the ratio of the premature is 100%, and then ratio of the older baby is 40%. 40% of the baby belong in this group. Okay, so that is because it's kind of like easier, not easy, but it can be a little bit complicated. But we have only two variables, so it's relatively easy to understand. But decision tree basically create these type of conditions and then create a tree. So I just bring those two-dimensional, you know, scatter plot-ish chart into the tree visualization. We're basically looking at the exact same thing. So we started with a bunch of babies at the top, like 25 baby, I think. And then the first question here is weight pound. Is the weight pound is greater than 5.5 or not? And then if it says 2, then all of them are actually not premature. So, and then it says 0%, right? And then this 0% under the blue circles are meaning basically like probability of the premature. So the probability of the premature is 0%. And then going to the right side, which is false. And then, so that one, it's not like 100%. They're mix, right? So it's like a red color and then blue color. There's a slightly mix. So like you want to ask another question, which is a plurality is greater than 1.5. And if the answer is yes, then I go to the left side, and then probability of premature is 100%. We can say 100%, okay, these guys or girls are going to be premature. And then the right side, like if your answer is false, then like 40% are going to be premature. That means 60% are not going to be premature. And then, so this is considered a tree, and then this is basically considered as a decision tree. Okay. So that's what the tree is. So now the question is, so how we build a tree, or how we don't build, the machine can build for us, but how the algorithm build this tree, how they design it. And the question is really, what we're talking about here is like, which conditions should come first, right? So like we had two conditions, like about the weight pound and also the plurality. So like so which conditions should we ask first, right? So that's where there's something called Gini impurity comes in. And this is, think of it as a score, a score to measure how much different values are mixed in each group. So each group, or like a node in the decision tree, right? So like when you ask one question, and then like after that, like you have the group 1 and group B based on the answer you gave to the question. And then in that group, like how much of the data is pure or not pure? Impurity meaning not pure. So like it's how much mixing in that data. So I'm going to upload this slide. So if you're interested in it, you can take a look at it. But just let me try to explain this more visually. So impurity equals 0. Just let's take that example. Meaning it's actually pure. Impurity is the opposite of the purity. So impurity equals 0, meaning actually super pure. So that means everybody is in one single thing. So in this case, particularly, is not premature. And then the formula is at the bottom. But impurity equals 0 can be the other opposite way. So if everybody is premature, then that also can be considered as an impurity score is 0. Okay, so now impurity equals 0.44 is kind of starting going up. Like I said, impurity is between 1 and 0 and 1. So the values start going up. Then that means premature, not premature, start mixing in. Okay, and then the opposite way, it can be the same thing. And then if you have a 0.5, that means basically half of them are, either group. So this is kind of like a very intuitive understanding of the impurity. It's about how pure the data is, and pure meaning just one single thing, or how not pure. That means like mix a lot of different diverse elements in the data. So let's try to kind of exercise this thing here. So starting point, let's imagine like we have the 10 babies, and then half of them is premature, half of them is not premature. Okay, so that means impurity is 0.5, right? And then now, if we start the question of the weight pound is greater than 5.5 thing first, then it becomes something like this. Okay. And then based on this particular data, okay, so it's not really, this data is not necessarily the exact same thing that we saw, but just imagine this is just an example. And then like, if the weight pound question actually separates into two groups, and one of the groups becomes just one single thing, and another group has two elements in the premature and the not premature. So that case, we can calculate the impurity, and the left side is 0 because everybody's blue, and the right side is mixed, but it's actually 0.41. And what we're going to do is we're going to get the weighted average between these two. And that equals 0.29. Okay, so that question, so that this 0.29 is the Gini impurity, or like how much weight pound can help to influence on the impurity score. Okay, so when we started it though, the impurity originally was 0.5. And now after asking this question of weight pound is greater than 5.5 or not, then the Gini impurity decrease about 0.21. Okay, so this question helps to decrease. So now like let's take a look at the other case. We could have like asked a plurality question first, right? So in the case, let's say plurality is greater than 1.5 or not. That imagine like we ask this question first, and we didn't ask the weight pound question yet. Okay, and this question turned out not really helpful, because look at these two groups after this question. Pretty much it's kind of like a mix. It's like a 40%, 60% mix, right? And then like when you calculate the impurity, both of them score the same. It's like 0.48. And then you get the weighted average becomes 0.48. And that means when we, compared to when we started it, where we started it, originally it was 0.5. And then now like we get 0.48. How much decrease? Well, that was only like, that is only 0.02. Okay. So this question has very small power compared to the weight pound questions. And this is a score that like a decision tree use behind the scene to figure out which question should come first. So based on that, and then it creates a tree like this. Then basically in the weight pound is actually, for example, this is like numerical columns or variable. So it detects where is, should create the line. For example, 5.5 is good, or 3.0 is great, or 6.0. that also try to basically get this better gene impurity score, and then like it also then start constructing the trees. And then sometimes the tree can have like a similar condition. So let's say like first, like you ask like a weight pound is greater than 5.5. And the next question could be, well, and then greater than 7 or less than 7, or like a greater than 3.0 or less than 3.0. So you're gonna, you can, in just some cases you see a similar question again and again, just that where you cut that numerical value can be different. Okay. And then just in case, like this is a tree could have been if we start asking plurality question first, and then it becomes something like this. But like we are not going to do be doing a business of like building a decision tree. That's what machine or algorithm can do for us. So, but I just wanted to show you guys how the decision tree algorithm works behind the scene. Okay, so enough about decision tree, and so let's get into like how to use this thing in Exploratory. Okay, so this is how to use in Exploratory, but pretty much like whatever the tool you use, you end up doing basically the same thing. Okay, so I have imported the US baby data. And then basically like what I'm going to do is I'm going to use this data first to just to give you guys a very brief idea. And then the second, like I'm going to move on to employee attrition data to try to build a model to predict who is, what type of employee tend to quit the organization or not. Okay, so let's start with US baby data first. So what we want to do, so this one is that each row is each baby, right? And then like where the baby is coming from, I was born, and then like what are the mother or father age, and so on. And then like one of the information is here. This is gestation week, right? So this gestation week, how many weeks the babies were in mother's womb before they're born, right? So like 38 weeks, 36 weeks, and so on. And then like when you look at this, like where's the gestation week? There you go. Histogram of the gestation week, and average is 38, and the median is 39. And then, like I said, like it's consider it according to WHO, like 37 weeks is whether you decide this baby is premature or not premature. So we want to create that column to before building that decision tree model. And by the way, decision tree doesn't have to be, it doesn't have to be always logical, like true or false. It can be used for, categorical. Let's say, for example, like a mother race name. If you want to build a model to predict which, race the mother would be, you can use that too. Or like you want to predict weight pound or gestation week, this is a numerical, you can use that too. But today, like I'm gonna create a logical column to see if this baby is premature or not, and then try to build a model to predict it. Okay. So to do either from summary view or table view, either way, from the column header menu, because we don't have that premature or not that information, so we need to create it. So let's create it quickly here, and select the mutate. This is where like you can create a calculation, right? Think of it as kind of like Excel thing. And then let's give a name, like is premature. That's going to be the new column. And then the gestation week is 37, less than 37, right? So this is kind of weird calculation because I'm just setting the condition. It's almost like the kind of condition that you see with a filter. But the cool thing about this mutate, or it's all happening R behind the scene, by the way. The cool thing about R is like you can create this kind of condition as a calculation. And what the R is going to do is give you return true if the condition matches, false if that doesn't. So that's pretty cool. So like, I'm going to just say like less than 37 and then click run. And what happened is basically it returns true or false. I think that table view might be easier to understand what just happened. So each baby gestation week was evaluated. And based on the evaluation, now like each baby has false or true, true or false values. And then this column is a logical data type. Okay, slightly different from the character. It's basically categorical, but it has only two types of values, true or false. And then when you go to the summary view, like you see, okay, so true, so basically premature babies is like 60,000, about something like that. And that is 11%, 12% of the babies are prematurely born. Okay. And then we want to basically build a model to predict if the baby is going to be premature or not. Well, we have all the information here, like answer here. So it's kind of like weird to say to predict, but imagine like we build a model, and then like there are a bunch of the new baby data comes in, and then like, that data doesn't have this column or even gestation week information. But then like we can use this model to predict, right? So that's one way to use it. But also another way to use it is to think, you remember like I was talking about a decision tree and how the decision tree was made. That means what are the conditions or questions are useful to separate the data, right? To make data more pure, right? So that means the decision tree is doing sort of like pattern recognition or like pattern finding. Right. So that it turned out is very useful, because if we know, for example, the weight pound is useful, then like that means the weight pound and then gestation week has a great correlative relationship. Or if let's say like mother race and it is premature, mother race is the predictor that is useful to predict is premature or not. That means this information itself has some correlated relationship with the gestation week or is premature, right? So those are the information that when you do the data analysis, we want to gain. Then like we can either predict or we can control to cause something type of output, right? So so anyway, so let's do build a decision tree. So go to the analytics view and then select decision tree here. And the random forest is right underneath, but that's for the next topic, next week topic, but today the decision tree. And then the target variables, this is where like you want to select our subject here. So this is premature. And then the predictor variables, and then let's select all of them this time, except this is gestation week. Because gestation week, if we know gestation week, it doesn't have to be machine, even can be human, can precisely predict, right? Because that is premature or not, that column was based on this gestation week information. So we definitely don't want to have the answer in the predictor. That's like, you know the answer before taking the test, right? So exclude that. And then, so basically like these are the variables that we're gonna, these are the base data we're gonna use to build a model. And click OK, and then click Run button. And that gives me this decision tree. And this is like super, like it's almost like you usually never see this kind of like a super simple tree. Typically you have a bunch of different branches. But nonetheless, we got this one. So first, let's take a look, try to understand what this is first. Okay, so this thing is very similar to what I was talking about here. Okay, so these three metrics I was talking about. So I'm gonna repeat that again. Here, the first one, this is true or false. In this case, basically we're trying to predict true or false values. So like you have only true or false. But this represents, hey, this group, what is the majority of this group? And the majority of this group is false. And the starting point, that means all the data. And which is at the bottom, this 100%. So 100% of the data to start with, of course, and then the majority of false. And as you remember, like when we started here is premature. Majority of this data, 500,000 babies are not premature, I mean like false. So that's basically what we are looking at here. And then here is a 12% is, this is a little tricky, but a 12% is true. Okay, so this second metric is always about the true, because we are trying to see like this like a logical column. So it's always try to predict if this is true or not. So that means 12% of the chance that this and that, this group of babies might could be premature. Okay, and then here we are asking a question. The weight pound is greater than 5.3 or no, and if the answer is yes, then here it becomes this group, and then red color group, this is false. Okay, so every time like you get confused, so when you look at this group, and its logical type is always red color is false and true color is blue, but even without the color, you look at this label, so this group is the majority is false. Okay, so like when you say like greater than 5.3 weight pound, that means pretty much not going to be premature. And then that babies are like among like 500,000, like 94% of the babies actually falls into this group. And then this middle one, 0.08, is like 8% of the chance this group might be premature or true. So let's try to do like another one here. So the first question is no, so that means less than 5.3 pounds. So it's pretty light babies, right? So light babies, and then those guys or girls can be, the majority are true. Okay, so less than 5.3 pounds and pretty much the premature baby. And then 6% of the 500,000 babies fall into this group. And 0.72, that is the probability of true. So in this case, probability of premature. So 72%. So if you answer this question no, then 72% of the chance that babies, we can say that babies are going to be premature. But very, very simple because we have only one single condition. But so that's what it is. And then when you click on this importance tab, this is where you can see the variable, something called variable importance. So which variables are more important to predict or better predictor? And then, you know, this basically, what's happening here is like, when you see like a higher one, in this case, like we have only weight pound and plurality. And even though like we had a bunch of other predictors, but like probably like the other predictors are not really helpful. So like if they're even ignored. And then like we have only this one. And then but in the tree, like we have only weight pound because pretty much most of the answers adding the plurality probably is not going to much change the quality of the prediction. So that's why. But I think the weight pound is significantly more important. And then like we can go click on this summary tab. And this is where you see some of the metrics to measure the quality of this prediction model. And then I'm going to go into more detail in next week of the random forest. But the one thing is very easy to understand is this accuracy rate, which is 0.90. And then the misclassification is the opposite. Okay, so 90% of the data, like this model can predict correctly. This is using the exact same data and build a model and then try to match that result with the training data. So, so we get that score. And then like, when you go to the prediction metrics, and this is where you can compare. So this model predicting true or false, and the actual, which is this data itself, and matching them. So that means, for example, if the model says true, and then the real answer is actually true, is 4.6% of the data falls into this category. And then when the model says false, and then actual is also false, is 86.37% of the data falls in there. Okay, and then here there's a little something called type 1 error, type 2 error. That's where things start getting a little interesting. But when you see something like this, which means here focus on this like actual answer is true, right? And then when the answer, the premature baby, in order to predict the actual premature babies, the model can perform is like 4.6% true, but also model also says false for 7.24%. This 7.24% is basically that this model is wrong to predict. it says false, it's not going to be premature, but it turned out it's premature. And when this number is bigger than this correct answers, and that's something that like you start thinking like, hey, what is going on? The couple things you can do, but like one of the things is when you look at this summary and then this recall, precision, F-score, I'm going to explain those things in the next session. So I'm not going to go into detail, but when you look at this, particularly this recall, the numbers, these scores is always between 0 and 1. But when you start seeing like something less than 0.5, it's like a 50%, and there's something going on. And in this particular case, though, just to give you a hint, this data is something called unbalance or imbalance, because only the 10% of the babies are premature. So that means if I was pretending like a machine, like just behind the machine, right? And then like if somebody asks me like this question, like I can say, you know, like, hey, the answer is false. I can always say false, right? No matter what. But still, I can be 88% or close to 90%, I'm going to be correct or accurate. And then this model, or machine learning, or even statistical model, when you have this kind of imbalanced data, start kind of like a skew towards to predict, building a model to predict the particular class or category, in this case, false. So that's why like here is basically this model, most of the time, it's like a 95%, oh no, sorry, 93% or something like that. This model is saying false, and then like it rarely says true. And then this happens with the imbalanced data. One thing you can do though is that from the property, there is a capability to adjust the imbalanced data. This is actually using this, some algorithm called SMOT, and then that's also like I'm going to cover that in a different topic. But basically, if you make this one like a yes, and then what's happening behind the scene is something called undersample. So like a majority here in this data is false. So like reduce the number of the false data, and then increase the number of the true data by synthesizing, finding kind of a similar data, and then make sure that it's not going to duplicate exactly the same data, but without breaking the pattern, and then try to synthesize, sort of like creating artificial data. And then like you get, go to the summary view, and F-score or recall precision increase, but then accuracy rate goes down. And that's because now it's not only always predicting false, but also now like predicting true too. So there are more chance to be wrong, but that is more something that like you would expect from the machine. Okay, so that's fine. The here is super simple, but it's always good to visualize, to understand what this really actually means, right? So when the machine learning model says, another thing I forgot to answer, tell you is that this analytics view, the default is sample size is 50,000, but this data is 500,000 rows or babies. So if we want to actually start increasing, let's say like, hey, I want to build a model based on 100,000 babies, or even like 500, whatever that is, you can use this field to change that sample size. Okay, but anyway, so let's go with this one though. So now the weight pound is seems like a default, and again, it's of course right. It's like if you know the weight pound, and then like if the baby is premature or not, like, of course. But just bear with me, just to simplify here. So how we can actually know if this is actually true, or like how this model is trying to predict or build a model. And it's always better to go to the chart and visualize. So here, what we want to do is, this is weight pound, right? So it seems like a weight pound 6.1 or like 5.5 or whatever the number is. It seems like that's where the sort of like a dividing line, and then makes a true or false. So what that means, there are different way to visualize this. So for example, let's do combination of data wrangling and the visualization. So weight pound, right? So look at here, I'm going to create the calculations. And then it says, it was like a 6.2 or something like that. 6.2, and then this is basically heavy or heavier, heavy baby, heavyweight, and then that is now true or false. Okay, so was that like a yeah, 6.1. Oops, so like go here. I'm going to change that to 6.1 and greater than or equal. Okay, so basically I created the exact same condition, and then like I like to see by, let's say, like a bar chart, heavyweight or not, right? The true or false. There are any data, so but we don't care. And then now like number of the rows. So like a true, so like this is like heavy babies, and then this is like light babies. And among these, like what are the ratio or how many of them are premature? So like I'm going to use the color, and then is premature or not. Okay. So now like this is like how many babies are premature now in each category, like a light baby and heavy baby. And I want to actually make this as a ratio. So like I can go to the y-axis and change the y-scale axis. So let's use the window calculation and then use the percent of. Okay. So forget that NA for now, but a true or false. So like if the baby is heavy, in this case, this true, right? This like x-axis is heavyweight. So like a true, then like 93% of the babies are not going to be premature because it's false, right? And then like here though, like light babies, like half of the babies are premature or non premature. So the 6.1 is basically, if you divide the weight pound, then like you can kind of see this difference. Another way is use a line chart. This is more like my favorite here. And what I want to do is the weight pound, instead of like making it into the categorical, just use weight pound as is. And then it becomes something like this. This is actually line chart. It doesn't look like line chart, but when you zoom in, it kind of like this. And that's because weight pound is like a super small number and decimal digit is super small. So therefore, like it makes pretty much nobody has exact same numbers. So to make it more like approximate, so like I'm gonna round this number just quick. Round using round counsel, round function, and digit is 1, and here is weight pound rounded, and that's the last column, right? So then now like, let's use that as x-axis, and it's gonna make looks like more like a line chart here. And then like y-axis is, so this is like a number of the babies we are seeing based on like weight pound, right? And then like category. And then y-axis, I'm gonna bring the premature or not thing. And then this is premature. So like this is, remember, this is a logical column, true or false. And when you assign it, and basically default is the number of true. So like we are seeing like number of true along the weight pound axis. But we can change that to percent of true though. Now, like what we are seeing though, at each point of the x-axis, let's say like this is like a 3.1 pound, and then a premature baby is a 92%, right? And then when you go down, it's around here. This is like a weight pound is 6. So when the baby is 6 pound, or like between a 6 pound and it's I think like 5.6 to 6.4 or something because we round it. But around that range, 20% of the baby is going to be premature. That means so less baby are going to be premature. So like we are seeing the percentage, or you can call it like a probability of the baby, a premature baby, start going down as weight pound goes up, right? And then basically the decision tree is trying to decide, hey, is this like a 6 is good, or 6.2 is good, or more like a 5 or 5.8? That's what the decision tree was trying to do. Okay, so but anyway, so in this case, pretty simple. It's the data is kind of simple because we have the weight pound, but typically you don't have that kind of predictor. So that's where like you see a bunch of trees. But important thing here is always make sure like you use the chart to visualize this. Then you can explain to other people, but also you can also understand intuitively. And then last topic now, let's apply this to, it's more realistic data. So here is employee data. And then each row is employee, each employee. And then like it has an information like age, or which department is working for, or she's working for, and the gender, and then and also the monthly income, and so on. And then there's one column called attrition. This is like basically labeling if this employee left the company or not left the company. True is meaning quit or left. Okay. And typically, though, this type of data that could be better to be applied with a survival analysis algorithm. But sometimes it's okay. We can use this kind of a classification algorithm. In this case, a decision tree too. But let's go with decision tree. So go to the analytics view, right? And we're going to do the same thing, the decision tree, and then target variable to be attrition, and a predictor to be, let's select all of them. And then I want to make sure like there was some kind of answer data is not here. Okay, looks okay. Then click OK, and then run the click run button. So this time it's a little bit more complicated tree, but it's actually not that complicated. So here the same thing. We always so this is like a true or false. So like a red color is false and blue color is true. So like first, when we started it, the majority is false, and then 100% of the data here, and then the percent of the true is 16%. That means 84% of the data is didn't quit. So like 16% of the people left in this data. Okay, and then like when you use the first question is overtime. So like if you work overtime or not, and then this is a little tricky. Like overtime equal no, that question, and then like answer is yes or no. So when you said yes, meaning overtime no is yes. So like you actually overtime equal no. Yeah. So like basically like these people go to here, this line didn't work overtime, and those people 72% of the data actually falls in here. So not many people overwork in this company, I guess. Then they're false, so that they didn't leave the company, they didn't quit the company. Okay. So, but then like we want to find, hey, what makes people leave the company, right, or organization? In that case, we can find this blue, right? These are the true ones. So let's say here, oh wow, this is like a true, and then the second one is 1.0, is like 100%. So whoever comes in this bucket, they're gonna leave 100%. And then, but the 1% is like only 1% of the employee falls in here. Okay. And let's take a look at what are the conditions. So like the first one, the overtime equal no is no. That means yes. It's a little kind of a twisted question here. But so these people did overtime, work overtime. And then monthly income, the next question is greater than 2,475. And the answer is no, because it always like a yes is going left and a no goes right. So like they're making less than $2,000, $2,400. And then the next question, the distance from home is this, I think is like a mile. So like less than 16 miles. And the answer is no. That means they live far. So they work a long time and then don't get paid. And then they live far from the office, and then they pretty much leave. And that's kind of intuitively like, yeah, of course. So those are the three conditions, right? And then like you can see like, what are the important stuff. For example, here is the monthly income is the defining the important variables, and then like overtime and job role and stock option level. And then the summary. So this one, like monthly income, I think the reason monthly income is the first one is because monthly income can be used multiple places, not just once. So first time here, a second one here, third one here. So that when you, some of the variable can be used multiple times, then it can becomes helps to this score higher. So that's why like you're seeing the monthly income first, and then like over time. But these are the important variables, and then this is like a quality of the model, and then a prediction matrix. And this again is imbalanced data. So like you see like a lot of prediction was down for like a false, like always the answer is false. So we can, adjust the imbalance data and so on, but we're going to just keep it for now as is. So now the last thing is like, so like how are we gonna visualize this? So like the first one, like is the overtime, yes or no, and then like we can basically match up with like attrition. And then so for example, a chart, and then a bar chart, and then like let's see, like this is actually kind of simple, like because it's categorical, like overtime, yes or no, and then number of employees, the y-axis, and then the color. Let's use the color and attrition. And then like let's use the window calculation to say percent of. And let's see like if overtime is yes, and then the blue color is the people who left. So like more people who left the company. So it's compared to overtime, no. So that's what we are seeing from here. Okay. And then next one is the monthly income, and then like distance from home. These two are numerical variables. So I'm trying to see, like maybe we can use like a scatter plot or a bubble chart. And this is where there's no one single answer. It's more like kind of like experimental thing. And then sometimes I get a good result, sometimes I no, but like let me try that like anyway. So here we can use a scatter, and then let's compare distance from home and the monthly income. And then maybe the color to be attrition here. And then basically the true people, so where the true people, the true people are the one who left the company. So let's say like here, do you see any like a trend? So like basically saying like when people are living far and then getting less pay, so like these people are going to be quitting. But there are other things too. So like let's see like what is going on here. And then like other thing we can do is instead of using this scatter plot is basically each dot is like each row or each employee in this case. We can actually kind of aggregate by sort of creating a binning. So in similar data, we can aggregate together. So in that case, we can use a bubble chart, and then group by is, for now, it's, let's say like a row ID is fine. And then distance and the monthly income, these are like right now like average, but instead of doing average, we can just do, let's say like integer or something. And then that's, we can see, like I think like over time is another question. So like over time, let's bring that to repeat by. Okay. And then what we are seeing here is that, so the true people, so where the true people are, and then what I see here, okay. So over time people, yes, and then what they do over time, and then distance from home. So like they live far, and then monthly income is low. So like around here, I think like what is condition here? Distance 16. So distance is 16 around here. So these are the people. And I think basically that's, if you belong in this area, and then pretty much, you're going to leave the company or something. So that's what's happening. And then let's say the number of the people. It's not, maybe, oh yeah, attrition. That's better. So here, let's do that. And then percent of the, what we want to do, the percent of the true. Okay, so now we are looking at here is, whoa, the size is too big. So I'm going to just change that to maybe 3. Okay, so this is the area. So definitely monthly income, if you're less than 2,000, and then like less than like 4,000, and then the size is decided of the percent of the true. So like percent of the probability of like people leaving the company, so it becomes higher than compared to higher area. And then the over time is like basically no or yes, and we don't really see the much difference between these two. It's kind of hard to see. but yes side. And then if there is any difference, x-axis is the walking distance from home. So like if you live kind of far, you tend to leave. But to me, it's a little hard to see the difference between, but I think this is what the model is saying. One thing though, this model is the data is imbalanced, so like we might want to adjust and then like rebuild the model and then get the different conditions and then apply that and then like try to understand by using the visualization. Okay, so that's like what the decision tree. So I went through the brief sort of like introduction of the decision tree, how it can be used, how you build a model, and then what type of insights you can gain from the decision tree. And then later on, like I introduce how to use the decision tree in Exploratory by using this analytics view. Okay, so I'm gonna stop here. And then what I like to do is open up the questions if you guys have any questions. Let's see. So here, got to go through. Okay, good. Yes, thank you. If you have any questions, I already made probably like all of you guys mute. So if you have any questions, click on the unmute button on the left-hand side bottom of this Zoom window, then speak up, or you can type the question in the chat window, either way, whichever works for you. Okay. Oh, thank you for leaving the kind words in the chat window.